Hello, this is Mr. Gisondo. We're going to be going through 8.1 today. If you don't know me, I teach Algebra 1 and I also teach Calculus. And a fun fact is my favorite animal is the ostrich, if you did not know. So we're going to check out 8.1, like I said. So 8.1, the whole topic is going to be about key features of quadratic equations, quadratic functions. For this one, you need to have notes and either Desmos or a TI grapher available, because this section, you do need to graph some things and see how the graphs relate. So we're going to look at parent functions. We're going to identify key features of parent functions. And a couple of vocab words we got parabolas and quadratic parent functions are the two vocab pieces. So if we start out, we've got the explore and reason sections first. Obviously, you can't do this with everybody, so we're just going to kind of do it quickly together. But we got two graphs. So here we can see our two graphs. We've got the absolute value of x, and we also have our new graph, which is x squared. So we want to find out which, with these two graphs, what makes them similar and what makes them different. So if we check it out, each of these graphs, they do start at the same place. So they both have a vertex at 0, 0, so that makes them the same. They both look like they can fold in on each other at that point too. So they're both symmetric about the y-axis, which is kind of interesting. Not all the graphs, especially all the linear ones that we did and the exponentials, they don't really fold into each other, but these ones do, so that's kind of cool. But they're a little bit different. This one you can see it's pretty sharp. This one's a nice smooth curve. So that's kind of a big difference. Is one is a very sharp V shape. That's the old one from chapter 5. And this is the new one that we have for this unit, which is going to be a nice U shape. So that's going to be our differences and our similarities. So we'll move on to example 1. So example 1 is where they start out with all the vocab. So the first thing it asks is what's the quadratic parent function and what are the characteristics. So the first thing we got is the quadratic parent function. So we want to get a good definition for that. Again, if you want to look in Pearson, you can grab the Pearson definition for that. But for the quadratic parent function, the whole idea is that it is just going to be any function that has the form f of x equals x squared. So that's what it's going to look like in equation form. A little bit different because, again, we're used to seeing the linear equations, which are just y equals mx plus b, or maybe the exponentials, the a times b to the x power. But this one's a little bit different. So this one we've got the quadratic functions. We got the little 2 as the exponent. And then these are going to make a different shape. Obviously, the linear functions made the lines. The exponential functions, they made kind of like the swoop. Some people said it looked kind of like those gamer chairs. Some people said it was just kind of like a little bit of a speed bump, but that's what those ones look like. For the x squareds, they're going to look a little bit different. They're going to look like parabolas. And we saw a parabola in the last part. A parabola is basically going to be any U-shaped graph. It's a U shape, it's not a V shape. So you got to be careful and make sure you don't pick anything that looks like a V, because V's are not going to be quadratics. So if we check it out, that's what our parabola looks like. That's what the parent function looks like. You can see the vertex is at 0, 0. That's all the way down here. Let me get my pen. So the vertex is going to be where it kind of looks like it folds in on itself, or it looks like the top or the bottom of the parabola is going to be. So that's going to be where the vertex is. So we say that the vertex is at 0, 0. The axis of symmetry is at x equals 0. Again, that's the part where we say it folds in around itself. So that's going to be right there, because it looks like we could fold that along that line. So we call that the axis of symmetry. We call it x equals 0. We do give the axis a whole line because we had to do a whole dashed line. It's not just a point. Like the vertex is just the top or the bottom. This is a whole line. It folds up around. And the last thing it says is that the parabola opens up. That just means it opens this way. So it's like a regular U shape. So that's what it means when it says it opens up. So that gives us a nice visual, because we want to look at it from a graphical standpoint. We've got our equation already, so we've got it from the equation standpoint. So the other way that we want to represent this is we want to represent it with a table. So over here we can see we've got our table. It's a little bit interesting. If we look at the table, we can see that our x values still kind of go the same as they did when we had the linear function. We go 2, -1, 0, 1, 2. But our f of x values, remember those are like the y's, they're not going up by the same amount. They're not going down by the same amount. They're not going in the same direction even. These ones go down and then it goes back up again. So we've got this U shape. So that's kind of the key for these ones, is that our y values, or the f of x values, they don't just all go in one direction like they did with the exponentials or the linears. They're going to go in one direction and then back again the other direction. And then here we've got the coordinate points, which are all the dots that are over here. Cool. So for the try-its, if you want to try it out, go for it. Just pause the video and go for it, but I'm just going to give you the answer. It asks, when are the values of f of x positive and when are they negative? This is kind of a trick question because the values of f of x are positive everywhere except 0, 0, because everything else is above the x-axis. So for f of x is positive, we go all the way from negative infinity all the way to 0, and then also from 0 all the way back to infinity, which means it's everywhere except 0, because remember at 0, we got 0 for f of x, so it's neither positive nor negative. So this is when it's positive. It's negative nowhere. It never goes below the x-axis, so the values of f of x are never negative. So that's kind of a little bit interesting too, because we expected a lot of those things, although we did see that with the exponentials. We had our asymptote where we didn't make things negative because we couldn't cross 0. In this case, yeah, it's not exactly an asymptote, but we can't cross 0. So for example 2, they want to look at the effect of a on the equation ax squared. So we're going to change the parent function a little bit because we're going to put a little a in front now. So they want to know how this affects the graph. So this is where you need to get Desmos or your graphing calculator. Desmos is nice because we can just go ahead and plop in ax squared. That looks pretty easy. So I'm going to turn it on, and that gives us our nice parent function. So that's the same parent function we had before. And we want to find out what happens when we change the value of a. So if we make it bigger, it's going to get skinnier. That's kind of weird because we're making that bigger. We kind of expect the parabola to get a little bit bigger, but it does. It just gets bigger in the y direction. It's like we're stretching our parabola out. So we kind of go like that with our parabola. If we take it down, we can see it gets a little bit wider. But that means we're going to shrink it vertically. So it's kind of like we're taking our parabola and we're just kind of squishing it. We'll go this way. So we can kind of squish our parabola. So that's kind of cool. So that's what we do with those ones. So that's how our leading coefficient affects our graph. If we wanted to write it, we could say that if a, if a is greater than 1, we get the vertical stretch. And if a is less than 1, but bigger than 0, because I didn't show you any negatives yet, we get a vertical shrink. So that's going to be what we have for our effect of a. Now, part B kind of gave it away, but part B asks what the negative sign does. So if you look at the graph here, you can kind of take a good guess. The red one's the original, the blue one's the negative. So what happens? It flips. It does a vertical flip. If you want to use the math term, we call that a vertical reflection, or a reflection around the x-axis. But it's a vertical flip. It flips vertically. So for the try it down here, again, if you want to do it, pause the video and think about it for a little bit. But it asks, how does the sign affect the domain and the range? Well, remember what we did is we went from a nice regular U to an upside down U. So the domain is the x's. That doesn't change because you can see we still go from negative infinity to infinity in both directions. We're still always going to go out in both ways. So the domain stays the same. But for the range is going to flip. So here, if we kind of set our parabola, it'll go like this. Our range was always positive, and now here, if we flip it, now the range is always going to be negative. So the range is going to be the opposite. So for example, if the range used to be y is greater than or equal to 0, if we change the sign, we get y is less than or equal to 0. So that's kind of cool. So it does affect our domain and range. So we talked a little bit about domain and range before. This is just reviewing domain and range. Example 3 talks about increasing and decreasing functions. So it wants to know over what interval is this function increasing? Over what interval is it decreasing? So it's nice if you have a graph representation, because you can just look at the graph and you can say, oh, well, here it's going down, here it's still decreasing, here it's still decreasing, here it's still decreasing, here it's still decreasing, and then it starts to change. And then from here, now instead of decreasing, now we're increasing, 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 because increasing, increasing, increasing. Because remember, decreasing means we're going down, increasing means we're going up. So it's not positive or negative, it's just increasing or decreasing. So we could say that it's increasing. Let's use the purple since I used purple for increasing. It's increasing when x is greater than 0. We would say it's decreasing when x is less than 0. Because here it's going down, and then here it switches to go back up. If we wanted to do that in a table, we could. We're going to do some fast math. So negative 2 squared is 4. 4 times 4 is 16. Negative 1 times negative 1 is 1, times 4 is 4. 0 times 4 is 0, times 0 is another 0. 1 squared is 1, times 4 is 4. 2 squared is 4, times 4 is 16. So if we do check, we can see here, we're going to decrease. Here again, we're going to decrease. But then, once we get to here, 0 to 4, we increase. 4 to 16 increases. So we can represent that with a table or with a graph. Again, when we had the linear graphs, sometimes we looked at the tables, and we just looked for the tables to see if there was that constant increase or constant decrease to prove it was linear, instead of just looking at the picture. So you can do the same thing with a quadratic. For the try it, we're given another form. It says ax squared is going to increase over the interval x is less than 0. So we know we want to go up if we're over here. And then we're going to decrease when x is greater than 0. So we want to go down over here. What's a possible value for a? So if we think about it graphically, we can make something that goes up and then goes down. That's not a very good parabola, but we'll say it looks more like that. So we know a has to be negative. That's the only restriction we have, though. We aren't given any other information, so you can pick whatever you want. I'm feeling like 3 is a good choice, so a is negative 3. I don't need the x squared because that's already in the problem. So a is negative 3. All right. For example 4, we're going to do a modeling problem. So we're given this nice little chart of a floor. So we're going to buy some flooring. We're told on the flyer it's $8.75 per square foot. So we refit our dance studio with new wooden flooring. So we have to find out how much we want to spend on the flooring, given that our room is a 15-foot by 15-foot room. So let's see. I'm going to model this first with an equation. So if I want to find the size of the room, it's a square. I know the equation for a square is that the area of a square is just the side length squared. So I know I have to pay for each square foot. I got to pay $8.75 per square foot. So my price is going to be $8.75 times whatever the area was, so times x squared. In this case, we've got a 15-foot side length. So x is going to be 15 feet. So that means my money is going to be 8.75 times 15 squared. All right, well, 15 squared, you might know that off the top of your head, but then multiplying that by 8.75, I think that's going to be a little bit rough. So we're going to go back to Desmos and plug it in. Look at that. We get 1,968.75. So 1968.75. Hopefully I remembered that right. 1978.65. 1968.75. Did not remember it right. That's okay. we can just change it, and that's why you always got to double check. Make sure that you actually write down what's on your calculator, because everybody makes mistakes. Oh man, I forgot again. All right, 1968.75. There we go. All right, and that's our result. So that's how much we would expect to spend. So we probably want to budget, since it's a real world problem, probably want to save $2,000 for it. For the try it, kind of a similar problem, but we want to increase the length of the dance floor by 2 feet. So this is where that advantage is, where I made the equation, because I know it's still, the money is still just going to be $875 times x plus 2 now. So x was still 15, so we could still plug the 15 in for the x. And again, I don't need to put 17. I can if I want, because I know 15 plus 2 is 17. But if I want, I can just throw it right into Desmos. Looks like I put the 17 in there. So we get 2,528.75. 2528.75. And again, did I remember right? 28,578. 2528.75. Not doing too good on remembering my numbers today. That's okay. There we go. But that doesn't answer the question. So that's how much it costs if it is 17. But the question asks, how much will it cost? How much will the cost increase? So I know how much it costs now. I need to subtract whatever it cost before. And again, I kind of forget. 1968.75. And again, I feel like that's something that's good for the calculator to do. So I put that in. I got $560 extra. So again, we have to think about this in case we want to have, a different room, because not all the rooms in the dance studio are going to be 15 by 15. So we got to think about it. What would happen if maybe we wanted to change our dance studio? Maybe we've got some ballet bars that we're going to take out, and that gives us an extra 2 feet of floor space that we then want to put some extra wood in. So something to think about. Last example is example 5. It talks about average rate of change. So we got to remember, back when we did linear functions, we called the slope the rate of change. So these parabolas don't really have the same rate of change, because we saw they increased or decreased by a different amount every time. So we want to look for an average rate of change. That means what we're going to do is pick 2 points on our parabola and just find what the slope is between those 2 points. So in the example that we got here, like if we looked at this 0.75x squared, I'm going to draw it really wide, even though it's not that wide. But we want to find the rate of change from when x is 2 to x is 4. So it's kind of like we're trying to draw a line between these ones. It's not a very good line. I want a different line. Where's the line tool at? There we go. So I want to draw a line, and you can see it doesn't exactly follow the curve, but I want to see what would happen, what the slope of that line would be. So what we're going to do is we're going to take our 2 points. We're going to take 2 and 4, and we're just going to plug them into the equation. So I'm going to plug 2 into the equation. I'm going to plug 4 into the equation. Now, if you want, you could do that all by hand. You could do 0.75 times 2 squared, which isn't too bad. But if we have a calculator, we may as well use the calculator. And so I put them all into the calculator. So I filled out my chart. Basically, I plugged in 2 into this equation, I got 3. Plugged 2 into 1.5x squared, I got 6. So 2, 6, 12, and 24. So we'll plug those all in. 2, 6, 12, and 24. And then I needed to find the slope. So I needed to find m. So just as a refresher, back from first semester, we had the slope equation was y2 minus y1 over x2 minus x1. So if I wanted to do it for the first one, I'd need to do 12, because remember, y is kind of the same as f of x, minus 2 over 4 minus 2. If you want to put it in your calculator, remember you need parentheses around each of those points if you got the TI calculator. And then same deal, we do the same thing over here. We do 24 and 6, but still 4 and 2 because we still have the same x's. Again, you could do those by hand. I put them into Desmos. So I got 4.5 and 9. So that gives us our two rates of change. So the slope here, which you can see, I really didn't do a very good job of it, but this slope is supposed to be 4.5. According to what we found out over here. So we want to find out how it compares. So if I compare 4.5 and 9, I could say 4.5 is 4.5 higher, but it makes a little bit more sense to say that 9 is twice as much. So it's twice as big. So g of x is twice of f of x. Which is kind of interesting because if we look at our initial a values, I think something's up there. So that's what it asks for in dot 2. It says, how does the rate of change relate to the values of a? Well, we know we got twice of f of x. 0.75 times 2 is 1.5. Oh, well, that makes a lot of sense. If we double the a value, our average rate of change is going to double. All right, so a kind of functions a little bit like slope. It's not exactly slope, but it does function as our rate of change. So it's the thing that dictates our rate of change. So the try it down here asks, how does the average rate of change for 0.05, negative 0.05 x squared, and negative 1.5 x squared compare? Well, negative not 0.05. Negative 0.5 there we go, times what number is negative 1.5? Well, if we divide both of them by negative 0.05, said negative 0.05, negative 0.5, 0.5, 0.5. So we're just solving a regular equation. We get x equals 3. So our average rate of change should be g of x is triple, because we get a factor of times 3, so g of x should have an average rate of change that's 3 times as big as f of x. So that's all the examples. That's everything from Pearson. They do go over the concept summary. So just to summarize the things that we learned about the graphs of the parabolas. So parabolas look like the U shapes. So that's what our parabola graph looks like. This is our parent function. We learned about what a did. So if a is negative, it's going to flip it. If a is going to be less than 0, it's going to make it a little bit wider. It's going to vertically shrink it. And if a is bigger than 1, so here we have 2, even though it's negative 2, we can kind of take the negative and the number as different things. It's going to make it a little bit skinnier. It's going to vertically stretch it. And that would be everything for 8.1. So hopefully you learned some stuff for 8.1. I'd recommend doing the practice problems that go along with 8.1 at this point, but it's up to you. Have a good day.